Today we're going to be solving the Physics Paper 1 2023 paper, so sit back, relax, and probably don't enjoy because it's physics and you just want to pass your exams and get on with life. So without further ado, let's get on with it. So question 1 is, which row contains only scalar quantities? So a scalar quantity is a quantity that has a direction. So let's go through these. A is temperature, which obviously can't be directional. Displacement is directional, so it's not this one. Cross this one out. B, acceleration has a direction because we can accelerate in different directions. Gravitational potential isn't directional. Kinetic energy isn't directional. Mass isn't directional, so it's C. Question 2, forces are applied to a circular shaft of diameter D. So we have a shaft here which has a diameter D. And we're applying a force, so which one of these equals a torque of a couple with magnitude force times distance? So when we're thinking about torque, it's only one of the forces we consider that goes... Sorry about that. It's only one of the forces that we take into the equation, so it's just singular F. And then the moment is F times D for this particular setup, so that would be B. Question 3. The resultant force acting on a moving object is 0. Which graph shows this? So when we have a resultant force, it means when the resultant force is 0, it means that there is no change in velocity, right? So the velocity is either 0 or it's not changing. So which one of these shows that the velocity either equals 0 or the change in velocity equals 0? So in A, the displacement is linear, which means it is constant velocity. So A. So moving on, question 4 is a stress strain graph. So describing the behavior of a material under load. So which row in the table correctly identifies the elastic limit, fracture, and ultimate tensile strength in the graph below? So we know that P is our elastic limit. So a material behaves elastically. So when a material behaves elastically, its stress to strain ratio is equivalent or proportional. And then anything after that is plastic behavior. So the maximum stress a material withstands is called our ultimate tensile strength, because it's tensile stress. So this is our UTS. And then our R is our fracture limit, which we can kind of tell by elimination. So which one is this? So P is, which one would this be then? So PQR is B. Question 5, a wire of cross-sectional area carries a load of 240 newtons. So we know that stress equals force divided by area. So this equals 240 divided by 3.9 times 10 to the minus 6, which equals 6.154 times 10 to the 1, 2, 3, 4, 5, 6, 7. So this is our stress, newtons per meter squared. Then our strain is giving us percentage. So because we have percentage, we can convert it by dividing it by 100, because obviously we times it by 100 to get the percentage. This is just saying that the cross section of the wire has extended by 0.3%, or like been squashed. So this is going to be 0. So for over 1,000, 0.3 times 0.003. So now elastic modulus, Young's modulus, is E equals stress over strain. So elastic modulus, which is and this is 2.05 times 10 to the 10. So C or D. So How do we know which one it is? Well, it says to an appropriate number of significant figures. So this typically means the minimum amount of significant figures shown in the question, which is 2. So it's a 2 sig figs. So it is going to be approximately 2.1 times 10 to the 10 newtons per millimeter squared, which is D. So question 6 asks us to find the change in momentum of the ball. So this is like the force impulse kind of question. So we know that force equals change in momentum divided by change in time. And with a graph of force against time, that is equal to the area under the graph. So we've split the area into 3 parts, one with a triangle, one square, and another triangle. So triangle 1, which is area 1, equals half base times height. So times the base is 10. So fuck off. 10 times 10 to the minus 3, and then times by the force of 45, which is 0.5 times 10 minus 3 times 45, 0.225. And then the area 2, which I guess we can put here, is just base times height, which is 45 times 70 times 10 to the minus 3, which equals 3.15. So frustrating. So it's more than 2.3, but it's obviously not in the magnitude of 2,300. I guess you'd get that if you forgot to times it by 10 to the minus 3 for the time, because obviously time's in milliseconds. So I guess we say it's B. So question 7 is a question on gravitational force and like what they exert. So we've got 2 spheres. So we've got one sphere and another sphere. They're the same size, so each mass is the same. Obviously I just drew them completely wrong size. So we've got a distance of 3.6 meters. So they're going to exert a force on each other because they have mass. What is that force? Well, our equation F equals minus G over R squared, which is this gravitational constant. The m's are the same, and the radius is the distance between the centers of the masses. So we can say that this is minus 6.67 times 10 to the minus 11. The masses are the same, so we can square it. And then the distance is 3.6 squared, which equals minus 6.67 times 10 to the minus 11. 3.9 minus 4, that'd be newtons. So we have a negative because they are attractive forces, so we can, and it's asking just for the magnitude, so the absolute number, which is 3. Yeah, so B. Sweet. It's always good when you actually get the answer. So part 8, question 8 is a momentum question, I guess. So we're going to write down our equation straight away. So momentum is mass times velocity. So we have initial velocity u, it bounces off q at angle theta. Okay, so the initial thing I'm thinking is if we write down magnitude, we want to find our momentum x. So momentum in the x direction. So obviously momentum is conserved. That's Newton's second law. So the momentum before is equal to the momentum after. So what's the momentum before? Well, they all have the same mass. So it's mass times velocity u equals. So what's velocity v? And so what are momentum p and q in the x direction? So this here is going to be, we've got like a triangle forming, don't we? Wow, I didn't know I did that. Okay, cool. So we have our opposite, our adjacent, and our hypotenuse. So for P, we're going to be using cos to find our x component. So that is going to be mv cos theta. And then for W, we use cos, but it's going to be, the angle is different. It's 90 minus theta, so we convert to sine because cos theta is equal to sine of 90 minus theta. That's a good tip. So that's plus W, MW, M sine. I'm writing out paper. So the m's cancel, so we get u equals v cos theta plus w sine theta. So one's wrong, so it's going to be 2 or 3. What else can we say? We can do it in y direction, I guess. So momentum y. So there's none to begin with. It's embarrassing. It doesn't even recognize my handwriting. Wow. Oh, it's because it thinks I'm writing momentum-y. So there's none to begin with. So 0 equals. So what's our up momentum? It's going to be v. So m the sine theta. So, yeah, the sine theta minus mw. We kind of established that it's going to be opposite now because of the perpendicularity. Yeah. So we're going to get mv sine theta equals mw cos theta. The m's are going to cancel. So w cos theta equals v sine theta. So that's right. U squared equals w squared plus v squared. We can think about kinetic energy, which is conserved. So we're going to get that half mass times u squared equals v squared plus w squared because our velocities are constant. That's a key bit of information here. So that is going to be half mv squared plus half mw squared. The half m's are going to cancel because they're all common. So we're just going to end up with u squared equals v squared plus w squared. Yes, so 2 and 3, C. So, question 11. A satellite is in geostationary orbit 36,000 above the Earth's surface. What speed is the satellite moving relative to the center of the Earth? Okay, so there are 2 keywords. It's geostationary and relative to the center, which isn't a word, but you know what I mean. So we have the Earth, big circle. We have like a nice little satellite, which I guess we could draw like this. So, because it's geostationary, it moves, so along the center. What the fuck? Sorry. Technical issue here. Okay. So relative to the surface of the Earth, it's. I'm never drawing arrows again. What the fuck? Good enough. So this is the same, right? The velocity is equal. Because geostationary orbit is like the whole point is a satellite can take like a constant picture of the Earth. But to the center it's different. So it's going to move relative. So this distance is from the center. And then it's going to go to the edge, which is. Alright, so our distances we're establishing. So this is 36k. This is 6,400 kilometers. So our R, I guess, is. I haven't actually read the question yet. I just thought. There's another 0 there. I could probably do that in my head, but it's late. 42,400 kilometers, eh? So, at what speed? So speed, distance is velocity, time. So velocity is distance over time. What's the distance? It's the diameter times pi, or 2 times the radius. So that's the distance of the orbit. of the orbit from the centre. So that is going to be 2 pi r over t, which I guess this t is the time period. So big T, which equals 2 pi times. The answer's in kilometres, so we don't need to convert that. And then a day is 86,400 seconds. I just remember that for some reason. 2 pi times 42,400 divided by 86,400 is 3.08, which is D. Question 12. Am I recording? Yes. Am I screen sharing? Yes. 12. I bet you, yeah. So we've got graphs of amplitude versus frequency. Heavily dampened. So what happens when we dampen a system? Well, the amplitude goes down. That's like the whole point. If you dampen a building, its building frequency decreases. I think I just lied. I don't know if the frequency decreases. Sorry, the amplitude of the oscillation decreases. What else happens? The frequency. What the fuck? I'm such a noob with an iPad. It's unbelievable. The frequency also decreases, like the maximum, the fundamental frequency. That's what I'm trying to say. Where the maximum amplitude occurs, so it also goes down. So the heavily dampened is where it's got the minimum amplitude and the minimum frequency, which is D. Question 13. Unlucky question 13. During the evolution of the universe, there's a period of inflation. Which forms of matter, if any, existed 10 to the minus 10 seconds after the Big Bang? So, knowledge drop. 10 to the minus 35 seconds equals inflation. Just like the economy, baby. At like 10 to the minus 6 seconds, we get our first fundamental particles. Which begs the question, why the fuck are we being asked this in this paper? It's paper 1. Knowledge drop. Leptons are fundamental particles. So 10 to the minus 10 is before. So nope. Atoms, even like later than leptons. Quarks are fundamental particles as well. Quarks make up hadrons. Quark plus quark equals hadron. Smiley face. So none of them. So it's none. That's boring. There might be another quark actually there. Anyway, I'm pretty sure quarks happen in thirds. It's probably know that. Emission spectra. Wavelengths. Right. So we have 434 and 486. What's the equivalent absorption? Knowledge drop again. 2 in 1 thing. 2 in 1 like page. When they're dark, it is emission. I don't know why. I just remember that there is. I can't draw that for me. When they're light, they're absorption. So it's we know it's C or D, right? So how do we actually know which one it is out of C and D? I spelled absorption wrong. There we go. Stop being fucking... Cool. Absorption. Fuck. What's the law? The Doppler effect, right? It's not a law, it's an effect. Might be a law. Sorry. So that states that the change in wavelength over wavelength equals V over C. So if our initial wavelength, or our 434, then our new one is going to be, so our change in lambda is going to be 434 times V over C. So V is 0.031 C. So I'm going to rub that out. I'm right. 0.031 C over C, which is cancel that bitch. It's amazing stuff. let's say a change in wavelength, which is like a number. 13. So our new wavelength is 447. They both have 447. That is really helpful. I'm looking at these numbers, by the way. 486. So we're going to do the same thing. So 486 plus 486 times 0.031 is going to give our new one, which is either going to be 499 or not, I guess. 501. So it's C. Great. Question 15. Hubble constant. Shit. So our Hubble constant is V, h0 over d. V here is recessional velocity, so the speed at what, like a galaxy's going away from us, I guess. So the Hubble constant estimated at 500. So h0 equals v over d. Got to do some thinking, right? So if this is velocity over distance, if distance equals velocity times time, then we get that time is distance divided by velocity, which is the opposite of h0. So 1 over h0 is time. But it's asking us to give it in per second, so that doesn't even matter. Great. So I guess we're just going to do some conversion. So 500, we've got to get rid of the kilometers, so we're going to times by 1,000. Then we've got to divide, because it's per megaparsec, which is 3.1 times 10 to the 16 meters. But it's a megaparsec, so we times it by 1,000,000. What the fuck? I went back a page. Which equals 1.6 times 10 to the minus 17. B. Is that the end? Yes, that's the end of the multiple choice section. Okay, so moving on to question 16. We have a diagram that shows a road with vehicles that travel at high speed. Okay, there's chevrons spaced at 40 meters. Drivers are advised to keep at least 2 markings visible on the road between them at all times. So 2 markings visible at all times. The vehicle in front, yeah. The maximum speed is 110 kilometers an hour. Here is some data. Calculate the maximum speed V of the vehicles of the road in SI units. Right, so we have a speed of 110 kilometers per hour. So to convert this, we need to do kilometers into meters. So that's going to be times by 1,000. And then hours into seconds, which is going to be 60 squared, because square seconds to minutes to hours. And that's going to equal 30.56. Here we are. So to 2 significant figures, I guess, because that's what the question says it is to. Well, that's the minimum significant figures in the question. 31 ms minus 1. A vehicle passes over one of the markings. Calculate the time to travel the 40-meter distance. So there's 40 meters. So we're going to use distance equals velocity times time. Rearrange for time equals distance over velocity, which equals 40 over 30.56, which equals 1.31. The time is 1.31. Next question, next part. Using the table, explain why having markings 40 meters apart help prevent collisions. So we've got a braking distance of 75 meters and a stopping distance of 96 meters. Basically, the cars have to be 80 meters away because they have to have 2 chevrons between them. So this is what we're looking at. So guess the first thing you can say is the stopping distance minus the braking distance is going to be the thinking distance. So what's that? 96 minus 75, that's equal to 21 meters. So 21 meters, is that enough time to think and to make a decision? So basically we've got to make sure that well, I guess because 21 meters is smaller than the 40 meters, so 21 meters is smaller than 40 meters, which is the distance between each one, so the driver has enough time to get out of the way. Driver has enough time to react. And then we can say that the braking distance is smaller than the 80 meters. So we can say that's 75 for braking. Smaller than the 80 meters between the two chevrons. And obviously the stopping distance is longer than 80 meters, but the car in front of them isn't going to just stop, like go from velocity is 110 to 0 in 0 seconds. So there is going to be deceleration. So the stopping distance can be the distance between the two chevrons can be smaller than the stopping distance. So B, so 3 points because it's 3 marks. So I was going to say those are the 3 points. This is going to be at F equals MA1, right? So yeah. So we need to find the acceleration because it's just a SUVAT. So we're going to say that distance equals, we don't know. U is 30.56. V equals 0. A equals, we don't know, but we want to find, and T equals 5.6. So we're going to use V equals U plus AT. So rearranging for A, that equals V minus U over T, which equals 0 minus 30.56. So it's going to be negative over 5.6. Because it's deceleration, it's going to be negative. That equals 5.46. So we're going to use the absolute value of A, so we're just going to use positive 5.46 because we can say it's accelerating at a rate of minus or decelerating at positive 5.46. So F equals MA equals 1600 times by 5.46, which is 8,736 newtons. So we're going to say 8,700. Explain the effect on the distance required to bring the vehicle to rest if the road has an upward slope. So if there's a slope, gravity is going to be working for you. So we're going to say, well, I guess we can say that some of the KE, kinetic energy, converts to potential energy. So we have energy lost. Thus, a decrease in velocity at a higher rate. As kinetic energy is proportional to velocity squared. Therefore, stopping distance is smaller. Right, question 16 done. Moving on to question 17. The diagram below shows a fairground ride. Each rider is secured to a seat suspended by a rod. 11.1 meters. The rod is attached to the edge. So we've got like a circular motion question. So what's question 1? Draw an arrow labelled T on the diagram to represent the tension in the rod. So the tension is going to be acting to, so we've got like a weight here, right? So we need the tension to resist that, so it's going to be going upwards. Show that the radius of the circular path followed by the sandbag is about 10 meters. Okay, so that's just asking that we have this. Why? And then we have, this makes a triangle. How have I done that? Don't worry. It's a triangle, right? We want to find the opposite here, 35 degrees. And then this is 11.1 meters. So we're going to use sine theta equals opposite over hypotenuse. So we want to find the opposite. So opposite equals sine theta times h, which equals sine 35 times 11.1, which is going to equal 6.37. So the radius is about 10 is what we want to show. So we're going to show that 7.8 over 2, which is the fairground diameter. Well, the radius over 2 plus 6.37 is hopefully close to 10. Which is 10.27 meters, which is approximately 10 meters. So that's AI and II. III is calculate the tension in the rod. So we're going to draw our triangle again. So we've got T here. This is our weight acting down. We've got 35 degrees here. This is going to be our centripetal force, which we don't need yet. So we've got tension, we don't know, but we know the weight is going to be the mass of the sandbag 12 times gravity. So W equals mg, which is 12 times 9.81. Which is 117, just say 118 newtons. So now we want to find T. So we've got adjacent and hypotenuse. So cos theta equals the weight over tension. So tension equals weight over cos theta, which is 118 over cos 35, which is 144 newtons. So what's the lowest significant figures? I'm seeing 2, I'm seeing 3. So we're going to say 140 newtons. Show that the angular velocity of the ride is about 0.8 radians per second. So angular velocity, what are the equations? So we got omega is 2 pi over t. But we can't use it because we don't have a rate of like oscillation. So we're going to use the centripetal force one, which is F equals, so this is the FC that we have, which is this guy. FC is m rho squared, why do I keep saying rho? M omega squared R. So FC is, now we need to find that sine theta is, in fact we're going to do tan because we don't know if tension's right. Probably is, I hope it is. Better be. But we know the weight, so it's just better practice. So tan theta is opposite over adjacent, which is centripetal force over weight, which is, so we can say that tan 35 times 118 is 82.6. So this is our centripetal force, and we're going to rearrange for omega. So omega is the square root of Fc over mr, rearranging the centripetal force equation, which is the square root of 82.6 over 12, the mass of the sandbag, times the radius, 10.27, which is 0.81 radians a second, which is good. It means it's right. When the seat is at its highest point, the sandbag is 17 meters above the ground. The sandbag is released from the seat to model an object being dropped by a rider. Calculate T, the time taken for the sandbag to reach the ground. So we've got this, it's going to be that projectile motion, right? we've got this motion. We want to find like this, the time taken to go that far, which is 17 meters. So we have S equals 17. U is 0 because it's from rest in the vertical direction. V is going to be a number. A is going to be 9.81. T we're finding. So we're going to use S equals UT plus a half AT squared. UT is going to cancel out because there's no U, it's 0. So we're just going to get S equals a half GT squared. Let's have the G in for A because gravity. So T is going to be 2S over G square rooted, which is, so that's going to be the square root of 2 times 17 over 9.81, which is 1.86 seconds. 1.9 seconds. So now we've got to calculate the horizontal distance, this guy. And we know the time, so we can just use, so velocity is constant in the horizontal in projectile motion. So just use distance is velocity times time, which is, the velocity is, we don't know, but we can work it out. Because velocity is omega r, which equals 0.81 times 10.27, which is 8.3. So now we've got 8.3 times 1.86 seconds, which we just calculated, which is 15.4 meters. So about 15 meters is what we're getting. Nice. So the last one is determine with reasons the effect of horizontal displacement travelled if the object released from the rider was a shoe from a rider. So I'd say that if it's the shoe, it's going to be like, so we've got the swing on the like thing. So we've got like the seat with the guy, and his shoes, right? His shoes are lower than the actual height. So this was originally like 11.1, I think it was. But now if this is longer, we're going to be closer to the ground. So it's going to be, H is going to be less than 17 meters, right? So what's that effect going to have? So the first thing that comes to my mind is because the height is less than 17 meters, time taken to reach ground is less. So if the time's less, as distance is proportional to time, horizontal displacement decreases, if that makes sense. However, it could increase, I guess, because now this length is greater than 11.1 meters. So this displacement here, so there's going to be a bigger radius, right? So this is going to be bigger than 10. So R is going to be bigger than 10 meters. And because velocity equals omega R, the velocity of the shoe is going to be proportional to the radius. So as velocity is proportional to radius and the radius increases, the horizontal displacement also increases because displacement's also proportional to velocity. Okay, so that is question 17 done. Question 18 is a 6 marker. Fuck. Okay. It's only gravity though, which is good. Method 1, vertical drop method. So we're just going to drop the ball and get the height from there, from different heights. Rolling ball method. Roll it down a 1.9 meter ramp, set different angles. Single sets are shown. The time was measured using a standard stopwatch operated by the student. So what we're going to do, we're going to compare and discuss the uncertainties of the two G values, and then describe how the student analyzes both sets of data. Okay, so starting off with uncertainties. Everything's measured with analog devices, so the uncertainty of the ruler to measure the, or the meter stick to measure the height is 0.01 meters. I guess the stopwatch is digital, but the uncertainty is going to be bigger than the 0.01 it would be for the, or 0.005 it would be for the time taken because of reaction time. So it's going to be bigger than plus or minus 0.1 seconds for human reaction time. This is going to be analog, so it's going to be 0.01. It's going to be plus or minus 1 for the angle, and again it's going to be bigger than plus or minus 0.1 seconds. So I guess we could, so we need 6 points roughly for this question. So 6 markers, 6 points, 6 marks. So the first thing we do to reduce uncertainty by collecting more data, I guess. We have one sample which is going to be very uncertain. I guess the other thing we can say is, because time will be longer, and distance farther, in the rolling ball method, it will be less uncertain. So if you think about it, the percentages are going to be of bigger values, so the percentage uncertainty is actually going to be smaller because each uncertainty will be a smaller percentage. So now we're going to discuss the analysis of both. So vertical drop method, assuming we have more data. Right, so vertical. So we're going to record at multiple heights. I guess we're going to plot a graph that looks like this. So on the y-axis, we're going to have height of the ball, and on the x-axis, we're going to have t squared, which I'll explain in a second. Because the only way we can work this out is using s equals a half gt squared, so the same equation we used in the last question. So where distance is going to be our height, right? So our gradient equals h over t squared, which is, so an h over t squared is equivalent to s over t squared, which is also equivalent to a half g. So we're going to multiply gradient by 2 times for estimate of, fucking hell, bad handwriting. I'm sorry about my handwriting, by the way. Just a bit different. So yeah, we're going to multiply the gradient by 2 for the estimate of the gravity. And for the rolling ball method, I guess we're going to use the same equation, s equals a half ut plus a half, wow, s equals ut plus a half at squared. We don't have a ut, but we can't say a is g yet, so we're getting at s equals a half at squared, so a equals 2s over t squared. So this is what we're going to use to calculate a. And we're going to plot, and then we've got to think about this. So this is our ramp at an angle theta, and we've got the ground here. Nice. We've got our ball here. So we've got our, so what we've got our component of weight here. So we've got W here, or sorry, oh yeah, we can say W. And then we've got our normal reaction force here. and then we've got a 90° here, because we want this guy here. We want this guy here parallel to the ramp, so we can find the component of force that's due to that's given the ball velocity, right? So this is 90 degrees.
No.
So, and this is our angle here. So we've got that. So this is going to be opposite, and hypotenuse is the mg. So W equals mg again. So we've got, and we can say that F equals ma. And we're going to say that mg sine theta, which is the force pushing the ball down, equals ma. And the m's are going to cancel, so a equals g sine theta. So when we plot a graph of sine theta against a, the gradient of the graph is going to be g sine theta, because a is equal to g sine theta over sine theta. So the gradient is going to be an estimate of g. On to the next question. 19. Describe how to find the centre of mass of a two-dimensional shape, including any equipment needed. So, this is going to be the plumb line experiment. So we're going to suspend shape from pin, basically so it's free to rotate. We're going to hang string from the shape, and draw a straight line. That's going to be over the shape, so this is called the plumb line, right? And then we're going to do the same thing, so we're going to like rotate the shape, basically pin from another corner. And draw another plumb line. Another plumb line. And then the intersection equals, the intersection of the lines equals centre of mass. Okay, question B. The bridge can be raised by an electric motor. 14 meters is the length, weight of 120 kilonewton, centre of mass is 6.3 meters. Calculate the average power required to raise the bridge to a vertical position. So we know that work done equals force times distance, W equals Fx. So the distance is, well the force, sorry, it's going to be 120 times 10 to the 3 times by the distance, which is going to be the 1.3 meters to raise it up, and then it's going to rotate 6.3 meters. So this is going to just be a constant radius. R equals 6.3 meters. So as it pivots around that pivot point, so the distance is going to be 1.3 plus the 6.3 to rotate, which is going to be 9.12 times 10 to the 1 to times to the 5 joules. So the power equals energy divided by time, which is 9.12 times 10 to the 5 over 90, which is 1.01 times 10 to the 4 watts. So it's just like 1.0 times 10 to the 4 watts. Suggest why the actual electric motor used to lift the bridge has a maximum power output several times larger than the calculated value BI. That's because system is not... Wait, my English is not good. Oh, doesn't even recognise what I've said. Isn't 100% efficient. So more energy required, more power required, I guess. And yeah, that's it. Right, so question 20 is a thermal physics one, it looks like. So a sealed container contains n moles of an ideal gas. The gas has pressure P, absolute temperature T, and occupies volume V. The mass of 1 mole of the gas is m. Use the ideal gas equation to show that the density rho of the gas is given by the expression rho equals, and then it's the ideal gas equation. So we know that pressure times volume equals number of moles times the molar constant times temperature. We know that density equals mass divided by volume. So we have volume here and we have volume here. So we want to rearrange for volume. So volume equals mass divided by density. And volume on the ideal gas equation equals nRT over pressure P. So then we're going to say that mass over density equals nRT over P. And then we're rearranging it for rho, which is, my bad handwriting, but it's this guy. So we need to put rho on the top and then rearrange. So we can say that rho equals, so we're going to times P to the top, so PM over, and then we're going to divide through by nRT. And obviously n is the number of moles, but it says it's 1 mole of gas. Oh, sorry. 1 mole of gas, so n is 1. So we can just cancel it out. So rho equals PM over RT. So we've shown it. B, an airship has a cabin suspended underneath a gas bag inflated with helium. The airship is floating and is stationary. The volume of the gas bag is 12,000 meters cubed. It has a temperature of 20 degrees Celsius. The temperature of the helium and surrounding air is 20 degrees Celsius. The atmospheric pressure is 1 times 10 to the 5 pascals. Molar mass is 0.029 kilograms per mole. Show that the density of the air under the conditions described is about 1.2 kilograms per meter cubed. So probably using this equation, density equals pressure times molar mass over R times temperature. So just sub all the ones in. So we've got 1 times 10 to the 5 times 0.029 over R, which is 8.31, times by temperature, which is 273 to convert to Kelvin, plus 20. And that's going to give us 8.31 times 273 plus 20. 1.19, which is about 1.2. So nice, we've solved that as well. Calculate the weight of the air displaced by the airship. So we have a volume of 12,000 meters cubed and a density of 1.2. So we can say that mass equals density times volume. So that equals 1.2 times 12,000. 1.2 times 12,000 is 14,400 kilograms. So we have the weight is mass times gravity, which equals 14,400 times 9.81, which is 1.4 times 10 to the 1, 2, 3, 4, 5. Okay, so the weight of the air is 1.4 times 10 to the 5 newtons. Next one is explain why the weight of air displaced by the airship has the same magnitude as the weight of the airship and its contents. So Archimedes' principle states that it's going to say that the weight of the airship is equal to the weight of the air displaced by the ship. Yep, so just replace ship for body, and that's literally what Archimedes' principle says. And because, remember, that the airship is stationary, we can say that the resultant force equals 0, so weight displaced, weight of ship equals weight of displaced air. Sorry about the room, I've got big handwriting. I don't care. Okay, so the pressure of the helium in the gas bag is maintained at a value only slightly greater than atmospheric pressure. It's just why larger pressure is not used. Well, that is because pressure increases density of the air. We need, actually it's pretty bad to say, we need to increase volume, or basically we say that pressure doesn't increase volume to create more upthrust, and that's again due to the Archimedes principle. So airship engine drives a fan of 7.8 kilograms of air per second. That's a relative speed of 45 meters a second. So the airship starts to move. All other conditions are the same as B. Okay. So we can say that change in momentum equals force times change in time. Time equals 1. So the change in momentum is the mass times the change in velocity, which is v minus u. So F equals, well, F times change in t is where t is 1, it's just F. So it's mass times v minus u. So F equals 45 times, sorry, F is the weight of the air moved, so 7.8 times 45 minus 0. Because the initial velocity is obviously 0 inside the airship relatively to where the airship's moving, which is 7.8 times 45, which is 351 newtons, so the thrust is 350. D, the airship has a higher maximum speed at high altitudes, but also produces less thrust from the engines. So higher speed due to less drag in a less dense atmosphere. There is literally less air pulling on the ship, but also the air, as the air is less dense, so basically the ship's moving less mass per second, so there's a smaller rate of change of momentum. And due to Newton's third law, so less force, as force is proportional to the change in rate of change of momentum. Done. Question 21 is oscillation related shit, probably. So figure 21.1 shows a stationary glider of mass m on an air track. The springs have a force constant K attached to secure posts. The air track blower is turned on and the glider is displaced a small distance x sub 0 as seen in figure 21.2. It is released. Using simple harmonic motion, the springs remain in tension throughout the motion. The time taken for 20 completed oscillations is measured and the period t calculated. The relationship between the period t, the mass of the glider m, and the force constant k is described by the equation t squared equals 2 pi squared m over k. Show that these equations are homogeneous by reducing the equation to SI base units. So this question asks us to basically show that the units on the left side of the equation are equal to the right. So time period squared is just seconds squared. And probably the more challenging part is to show that 2 pi squared m over k is equal to time seconds squared. So pi is unitless, so we can just say that the top mass equals kg, and k is probably the harder one. So we know that F equals kx, so k equals F over x, which is, and Newton is like mass times acceleration, so kgms minus 2 divided by the x, which is displacement, which is meters to the -1 because we're dividing, so those cancel. So now we're left with kg on top from the mass, and the k is equal to kgs minus 2, these cancel, and it's just 1 over s minus 2, which equals s squared. So yeah, that's the same as t squared. So that's solved. Explain why the magnitude of the resultant force F on the glider is given by F equals 2kx, where x is displacement at any time. So force equals kx, and then I can just say both strings have this. Have the same but opposite extensions. So you can say that the change in force is equal to the change in basically the extension, and that is equal to k positive x, and then obviously one's going the opposite direction, so it's going to be a minus displacement, because I guess you could say that it's positive, so this, and then so this one's getting, probably make more sense to do it this fashion. So this one's getting a smaller extension because it's being compressed, and this guy's getting elongated, so it's got a positive extension. But the difference is kx minus k lots of minus x, because it's got a minus displacement, which equals 2kx. So F equals 2kx. State and explain the effect, if any, of increasing the initial displacement on the period of the subsequent motion. So period is exclusive, I guess, of displacement, so not affected. My bad handwriting. Okay, so if you think about it, if you just pull a string more, it's just going to release with a faster acceleration, so the actual time period is going to be the same anyway, even if the displacement's longer, so the period remains the same. Obviously there's factors that can change it, but this is an idealized situation. So we've got a table, we've got to describe two errors straight away. Time period t/t squared should have units. And then we've got these guys, which should have all data should have the same significant figures. Nice. So plot the first data point on the table of the graph below. So 0.2 kg has a time squared of 0.372. So at 0.2, use about that, as a one of 0.372. So each increment is 0.32, 4, 6, 7. So it's about this, and it's going to be across here. And then the straight line is probably going to be about this. Which looks good. Yep. So now we need to use the graph to determine k. Okay, so what, as our original formula was t squared equals 2 pi squared m over k. So t squared equals 2 pi squared m over k. So we've got to think, what is the gradient of this graph going to be? It's going to be t squared over m. So gradient yep. So t squared over m equals 2 pi squared over k. So gradient equals 2 pi squared over k. Okay, so k equals 2 pi squared over gradient. So what's our gradient? It's changing y divided by changing x, which is, so our biggest y we can say is from here and then, okay, that's fine then. So what is this? This is about, oh, okay. This point here is 1.0020424. So that's like 1.0, oh, my bad. It's 1.05. This guy here is about 0.1. That's about 0.12. And this guy here is about 0.6, 0.7, 0.7246. 0.72-ish. So the y, change in y is 1.05, take 0.12. That's over 0.72 minus 0. So over, which is 1.29. So k equals 2 pi squared over 1.29, which is 15.3. So okay, our spring constant is about 15. Pardon me. When the initial displacement is increased, one spring increases its extension while the extension of the other spring decreases. That's like that first thing we said about. Why is the kinetic energy of the motion increased? So the first thing I'll say is the potential energy from stretching the spring. So the gained potential energy from stretching the spring has to exceed the PE lost from the slack spring, I guess you could say. This has to be true for the kinetic energy to increase. So the elastic potential energy is equal to 1/2 kx squared. So if the initial displacement increases, so as EPE is proportional to x squared, EPE increases if displacement increases, which it's saying it has. So this hasn't to do with kinetic energy. So as we can remember, for example, like a pendulum, it's like the easier one to think about. It's like at the top it has max PE, and at equilibrium it has max KE. So more potential energy means more transferred to kinetic energy during oscillation. Fucking hell. Explain why the maximum kinetic energy. So yes, so we get a higher potential energy because of the displacement. So now we've got a higher kinetic energy, and we can say that at equilibrium, God, I'm giving up writing, where x is 0, the maximum velocity is released or reached. And then we can say that KE is equal to 1/2 V squared, mv squared. So KE is proportional to V squared. So if V is higher, KE is higher. Question 22. A star has a mass similar to that of a sun. So it's a low mass star. Describe how the position of the star in the Hertzsprung-Russell diagram changes as it evolves. So figure 22.1 is a blank Hertzsprung-Russell diagram. We've got figure 22.2, which looks like it's going to be Wien's law type shit. And we've got to explain how this guy here is can help us find what stage of evolution at the star is. So Hertzsprung-Russell diagram quickly is going to be supergiants that are the most luminous and most bright. So kind of in this gap here. Then we have giants, which are just a little bit cooler. And we have main sequence stars, which kind of go down and right. They kind of fill in this. And we have dwarfs, which are the coolest and least luminous. So our dwarf stars are white dwarfs and our black dwarfs. Okay, so because the mass is similar to the sun, it's a low mass star. Which means it evolves first to a giant, just a regular giant, and that's when it runs low on hydrogen. Then when it starts running on helium, then it evolves to just a white dwarf. So remember, the supergiant stars are the ones that go supernova and turn into dark holes and black holes and stuff. So it's a white dwarf when it's still hot, and then it cools over time and turns into a black dwarf. So on the Hertzsprung-Russell diagram, it's going to look a little bit like this. So it's going to go up the main sequence as it cools. It's going to go to the supergiant, sorry, the giant, and it's going to go back down to the dwarfs. So that's about the pattern it's going to take. We can make it a bit like this. Okay, so onto this one. So the kind of thing that governs this is max wavelength is proportional to, or inversely proportional to temperature. So we need to find whereabouts the peak wavelength happens and how luminous it, and that shows how intense it is. So if a star has a shorter wavelength, it's hotter, right? Because lambda max, so the smaller this is, the bigger the temperature is going to be, to keep B constant, which is, what that is, it is 2.9 times 10 to the minus 3 millikelvin. So that's constant. So obviously the opposite's true. If the peak wavelength is at a bigger wavelength, it's going to be a cooler star. So we can use this to find that we can do that lambda max times by temperature is equal to B, which is 2.9 times 10 to the minus 3. So we can rearrange this for T and find horizontal coordinate of HR diagram, Hertzsprung-Russell diagram. Sorry. So yeah, this is going to be this temperature. So we don't know how far up or down the temperature is, and this is what we can use to find it. So now we've got to say, describe the limitations of the analysis. So we have the horizontal, we have the x coordinate of the graph, but there's no way for us to find the luminosity. So we're going to say we have no way to find luminosity. This means we can't distinguish, so can't distinguish between similar temperature stars. And yeah, that's question 22 done. Question 23 is Hipparcos Space. The Hipparcos Space Telescope used stellar parallax with a precision of 9.7 times 10 to the minus 4 arc seconds to determine the distance to the stars. One of the stars was Polaris A Data. One of the stars was, God, it's late, isn't it? One of the stars studied was Polaris A. Data about this star is in the table below. So we're given the parallax angle, the radius, the mass, the temperature, the surface temperature, and the temperature in the atmosphere. So AI is to estimate the maximum stellar distance in parsecs that could be measured using Hipparchus. So we have the equation that 1 over the parallax angle equals the distance in parsecs. So we're given that Hipparchus has a precision of 9.7 times 10 to the minus 4, which means that this 9.7 times 10 to the minus 4 is the smallest possible reading. And because it's the smallest possible reading, it means that D is going to be a maximum as P is at a minimum, right? So we're going to rearrange for this. So D is going to be 1 over P. So 1 over 9.7 times 10 to the minus 4 equals 1031 parsecs, which is about 1000 parsecs. So the percentage uncertainty is going to be the possible difference in values versus the actual value of the parallax angle. So the precision is 9.7 times 10 to the minus 4, so that's going to be the difference, because that's basically the increments that the telescope makes readings at. That's going to be just simply over the parallax angle we recorded times 100 to convert it to a percentage, which is 12.9, so about 13%. B. A continuous stream of particles called the solar wind flows from the surface of the star into the surrounding space. These particles include helium nuclei of mass 6.6 times 10 to the minus 27 kilograms. So we're getting temperature in the atmosphere. So the atmosphere is 4 times 10 to the 6 Kelvin. So T equals 4.0 times 10 to the 6 Kelvin. And the equation for kinetic energy when we're talking about these gases is E. Sorry, I forgot. You derive this using the root mean square. E equals 3 over 2 kT. And like this is just derived using the PV equals a third mc squared, and then PV equals mkt. So if you equate those, you rearrange it to get the kinetic energy. So this equals 3 over 2 times the Boltzmann constant, which is where is it? 1.38. I should know that really. 1.38 times 10 to the minus 23 times by 4 times 10 to the 6 Kelvin, which is 3 over 2 times 1.38 times 10 to the minus 23 times 4 times 10 to the 6. I completely messed that up. 8.28 times 10 to the minus 17, which is just 0.02 times 10 to the minus 17 off 1 times 10 to the minus 16. So this is about 1 times 10 to the minus 16. Because imagine this is about equal to 10 times 10 to the minus 17, which is equal to 1 times 10 to the minus 16. Okay, so that's proved. That's good. So the next bit is the gravitational potential energy of a helium nucleus is in the outer layer of the star is minus 2.3 times 10 to the minus 16 joules. Calculate the potential energy U at the maximum distance from the star. Right, so we have a star here, and then we have like its atmosphere here. So at the surface is here, and once they get out, so this radius is going to get bigger, right? So if we use the equation E equals minus GMM over R, which is gravitational potential, you can see that as R increases, E is going to decrease. So as R is going to increase, as the helium nucleus is getting further away from the center of the mass, E is going to like get towards 0, right? So our kinetic energy is 8.28 times 10 to the minus 17, and we're going to add that to the gravitational potential energy, as there's going to be a transfer in energy, right? So all the kinetic energy is becoming potential energy. So we're going to say that GPE plus KE equals minus 2.3 times 10 to the minus 16 plus 8.28 minus 1.5 times 10 to the minus 16, which is minus 1.472 times 10 to the minus 16. So this is our maximum GPE, right? So now we're going to use this guy to calculate the distance. So if E is equal to this, minus GMM over R is going to be equal to minus GMM over E, which is equal to minus 6.67 times 10 to the minus 11 times by the mass of the star, which is 1.1 times 10 to the 31, times by the mass of the helium nucleus, which is 6.6 times 10 to the minus 27. This is all going to be over the energy we just calculated, which is minus 1.5 times 10 to the minus 16. And that's going to equal 3.23 times 10 to the 10 joules. So 3.2 times 10 to the 10, sorry, meters. IV is explain why the star has a solar wind that reaches a much greater distance from the star found in III. So basically the velocity we calculated isn't the max velocity, right? Because the way we derive the kinetic energy is using the root mean square, so the mean velocity. So KE calculated using mean velocity. So in reality, some particles will be traveling much faster. So will reach a greater distance. And yeah, that is the end of the paper. Thank you for watching this far if you got here.